What happens right away if we deorbit the ISS early? The moment that decision is made, a complex and irreversible sequence begins. It is a process governed not by panic, but by the cold, hard laws of physics and the intricate web of human agreements. This is not a sudden catastrophe, but a meticulously planned conclusion to one of humanity's greatest collaborative achievements. The International Space Station, a beacon of cooperation shining down on us, has a finite lifespan. Bringing it home ahead of schedule is a monumental task, one that requires a global consensus and a deep understanding of the forces that have kept it aloft for decades. The first step is not a physical action, but a cascade of communications across continents and space agencies. The initial phase is a comprehensive review. Engineers and mission controllers would immediately begin assessing the station's health and resources. How much propellant is available for the deorbit burns? Which life support systems are fully operational, and which are nearing the end of their service life? Are the communication links stable enough to manage a complex multi-stage descent? This is a system-wide audit, a final inventory of a home that has been continuously occupied for more than 2 decades, all while traveling at 17,500 miles per hour. The results of this audit would dictate the entire timeline. Ultimately, the first immediate outcome is the creation of a definitive plan. The timeline for undocking any remaining crew or cargo vehicles, and the exact coordinates of the targeted re-entry corridor over the South Pacific Ocean. It would establish safety zones, communication protocols, and contingency measures for every conceivable failure. This plan represents the transformation of a hypothetical what-if into a concrete set of actions. It is the moment when the abstract idea of ending the mission becomes a real, tangible engineering problem with a firm deadline. Simultaneously, diplomats and agency heads would convene. The ISS is not owned by one nation, it is a partnership. The legal frameworks and international treaties that brought it into existence also govern its end. To understand how to bring the station down, we must first appreciate what keeps it up. The International Space Station exists in a perpetual state of falling. It is constantly being pulled toward the center of the Earth by gravity, the same force that keeps our feet on the ground. So, why doesn't it crash? The answer is its incredible speed. The station is hurtling sideways at about 5 miles per second. This immense horizontal velocity means that as it falls, the curve of the Earth drops away beneath it at the exact same rate. This delicate balance between forward momentum and the downward pull of gravity is what we call an orbit. To counteract this orbital decay, the station must periodically get a boost. This is achieved using thrusters on the Russian Zvezda service module thrusters on visiting Progress cargo spacecraft. These engines fire in short, controlled bursts, a process known as a reboost burn. These burns add a small amount of speed to the station, pushing it into a slightly higher, more stable orbit. Mission planners carefully schedule these reboosts to maintain the station's operational altitude. It is a constant, gentle push against the inevitable pull of our planet, a continuous dance to keep this outpost in the sky. The concept of deorbit is simply the reverse of this process. Instead of firing thrusters to speed the station up and raise its orbit, a deorbit maneuver involves firing them to slow it down. By applying a braking force, mission controllers intentionally reduce the station's orbital velocity. This tips the balance of forces in favor of gravity. With its forward speed diminished, the station can no longer outrun the curve of the Earth. Its path begins to curve more sharply downward, initiating a final, controlled descent. The same engines that keep the station alive are the very tools used to guide it to its final resting place. The International Space Station is not governed by a single entity. It is a consortium, a testament to international cooperation. The primary partners are the space agencies of the United States, Russia, Europe, Japan, and Canada. Each partner owns and operates different modules of the station. That distributed ownership means any major decision, especially deorbiting, must be collective. No single country can unilaterally decide to bring the ISS down. The process is rooted in decades of international agreements. A formal timeline starts with a proposal from one or more partner agencies. Trigger: major technical failure deemed irreparable. Trigger: significant safety risk to the crew. Trigger: collective judgment that science and finances no longer justify operations. Then high-level meetings between agency heads would commence. They would review technical data safety assessments and budgetary implications. National interests are weighed against the partnership's collective good. Final authority rests with partner governments, guided by their space agencies. The foundational document is the ISS Intergovernmental Agreement signed in 1998. The treaty outlines responsibilities for operations and eventual disposal. Any deviation from the agreed end of life, currently targeted for around 2030, would require a formal amendment or consensus via diplomatic channels. The process is slow as governments align policy and budgets. Delays are likely as nations negotiate roles and contributions to the deorbit. Roles are defined. NASA, Roscosmos, the thrusters for final deorbit burns are on Russian modules and Progress vehicles. Therefore, Russian cooperation is a technical necessity. NASA has developed detailed deorbit plans and could commission a specialized deorbit vehicle. ESA, JAXA, CSA. Their agreement is essential for an orderly, unified conclusion. Deorbiting a structure the size of a football field is a delicate and complex ballet of orbital mechanics. The process begins long before the final burn. First, the station must be prepared, shutting down non-essential systems, securing loose equipment, configuring the station to be controlled remotely from the ground. If astronauts are still on board, their safe departure is the absolute first priority. Crewed spacecraft like SpaceX's Crew Dragon, Russia's Soyuz would undock and return to Earth, leaving the station empty for its final journey. This departure phase itself is a constraint, as it depends on the availability and readiness of these return vehicles. The core of the deorbit procedure is a series of precisely timed engine firings breaking burns. These burns are designed to lower the station's perigee, the lowest point in its orbit, into the upper layers of Earth's atmosphere. The amount of fuel required is immense. Engineers must calculate the total change in velocity, or delta V, needed to bring the station down from its operational altitude. This calculation determines how many Progress cargo ships loaded with extra fuel might be needed to dock with the station to assist in the final push. If there isn't enough fuel, the entire plan must be re-evaluated, potentially leading to delays while more resources are sent up. These braking burns are not performed all at once. They're spread out over a period of days, even weeks, gradually shaping the orbit. Mission controllers on the ground will send commands to the station's computers, which then fire the thrusters for a predetermined duration. Sophisticated tracking systems on Earth will monitor the station's trajectory after each burn, verifying that its path is changing exactly as predicted. If there are any deviations, subsequent burns can be adjusted to correct the course, ensuring the final entry point remains precisely targeted. The final burn is the most critical. This is the point of no return maneuver that commits the station to its atmospheric re-entry. It must be timed perfectly to ensure that the station's debris field falls into a pre-designated remote area of the South Pacific Ocean. This location, known as the spacecraft cemetery, is chosen because it is the largest uninhabited stretch of ocean on the planet. The final burn must be powerful enough and long enough to lower the perigee, sufficiently ensuring that atmospheric drag will quickly and decisively pull the massive structure down along a predictable path, minimizing risk to life and property on the ground. The immediate consequence of the final deorbit burn is a dramatic and unavoidable atmospheric re-entry. As the ISS descends into the denser layers of the atmosphere at thousands of miles per hour, the friction with air molecules will generate immense heat. The station will begin to glow, becoming a man-made meteor streaking across the sky. Aerodynamic stresses and extreme temperatures will cause the structure to break apart. Solar arrays will be torn away, modules will separate, the station will disintegrate into a cascade of smaller pieces. Most pieces, especially lighter aluminum components, will completely vaporize in the intense heat. However, the ISS contains many dense, robust components made of stainless steel and titanium. These include docking ports, gyroscopes, and parts of the main truss structure. These heavier pieces are likely to survive the fiery plunge and reach the surface. To manage this risk, the entire deorbit is planned around a specific landing corridor. This corridor is a long, narrow ellipse stretching for thousands of kilometers over the South Pacific Ocean uninhabited area, the spawway. The goal is to ensure any surviving debris falls within this designated zone, far from land and shipping lanes. To ensure public safety, international authorities will establish extensive exclusion zones for the duration of the re-entry event. Air traffic controllers will divert all aircraft from the airspace above and around the re-entry corridor. These safety zones are not suggestions, they are mandatory restrictions to eliminate any chance of a collision. The timing of the final burn is calculated down to the second to ensure the debris footprint falls squarely within this protected area. The world will be watching, and accuracy is paramount. Predicting the exact breakup behavior and debris spread is a science in itself. Engineers use complex computer models to simulate how the station will disintegrate. These models use thresholds for material strength and thermal resistance to forecast which parts will survive and where they might land. Even with the best models, there are uncertainties. Atmospheric conditions, the station's exact tumble rate as it falls, and how it initially breaks apart can all influence the final debris pattern. Because of this, the safety corridor is made intentionally large to account for these variables, providing a wide margin for error and ensuring the safe conclusion of the station's mission. An early end to the ISS mission would send shockwaves far beyond the aerospace community. The most immediate impact would be the loss of a unique scientific laboratory. For over 2 decades, the station has hosted thousands of experiments in microgravity, medical research, bone density, medical research, immune function, materials science, Earth observation. An early deorbit would mean the abrupt termination of these long-term studies. Datasets would be left incomplete. Years of research by scientists around the world would be lost. This is a significant setback for many scientific fields that rely on microgravity. This scientific loss creates a powerful ripple effect on funding and incentives. Government agencies, private institutions. With no destination for their experiments, the incentive to fund this type of research would diminish. Early deorbit, loss of research platform, reduced funding for LEO science, delay in new technologies. Budgets might be redirected away from human spaceflight research, toward robotic missions, or toward ground-based science. This shift could create a lost generation of microgravity researchers, and slow discoveries in human health and in advanced materials. The feedback loop is simple: no lab, no experiments. The commercial space industry would also face a major disruption. Launch providers, SpaceX, cargo resupply, Northrop Grumman. The station is their most important and consistent customer. An early deorbit would eliminate that guaranteed revenue stream. That could jeopardize the financial stability of these companies. This could delay development of the next generation of commercial space stations. The loss of the anchor tenant creates market uncertainty and can make investors hesitant. The impact on international partnerships cannot be overstated. The ISS has been a cornerstone of space diplomacy for a generation, a symbol of post-Cold War cooperation. Ending the mission early would require navigating a complex political landscape. Each partner agency has invested billions of dollars and decades of work. An early termination could create friction and strain these long-standing relationships. The process of negotiating the end would test the strength of these partnerships and could influence the structure of future large-scale international collaborations in space and in other fields of science and technology. The deorbit of the ISS, whether early or on schedule, marks the end of one era but also forces the beginning of another. The long-term consequence of its absence is a fundamental change in the landscape of human activity in low Earth orbit. For years, the ISS has been the sole destination for astronauts from many nations. Without it, humanity's continuous presence in space, an unbroken chain since the year 2000, would be paused. This creates a gap. The question is, what will fill that gap, and how long will it take? The answer depends on a feedback loop between technology development and investor confidence. One possible future involves a transition to commercially owned and operated space stations. Several companies are already designing these private outposts, intended to serve as destinations for national astronauts, space tourists, private researchers. An early ISS deorbit could accelerate the demand for these platforms. However, it could also have the opposite effect. If the ISS is decommissioned before these new stations are ready, the resulting gap could erode market confidence. Without a proven destination, potential customers may be hesitant to commit, and investors may pull back funding, creating a delay that prolongs the gap in LEO access. This potential gap has significant consequences for the entire space exploration ecosystem. The ISS serves as a crucial training ground for astronauts and a testbed for technologies needed for long-duration missions to the Moon and Mars. Without it, NASA and its partners would lose their primary facility for preparing for deeper space exploration. This could delay ambitious programs like Artemis, which aims to establish a sustainable human presence on the Moon. New training protocols would need to be developed. Technologies for life support and radiation protection would have to be tested in other, perhaps less ideal ways. Ultimately, the altered state of LEO will depend on strategic decisions made today. Will governments choose to fund a seamless transition by directly supporting the development of commercial stations? Or will they accept a temporary pause in human LEO activity to focus resources on lunar and Martian missions? The path taken will shape the space industry for decades to come. An early ISS deorbit would force this decision upon us sooner than planned, transforming a distant strategic choice into an urgent tactical problem. How will the international partners and the burgeoning commercial space industry balance the immense risks, the staggering costs, and the invaluable scientific knowledge at stake when a shared global asset as magnificent as the International Space Station must finally come home? What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.